Today's instructional walkthrough presentation introduces you to the helper function in the 3D ACIS Modeler that greatly simplifies the multi-threading of ACIS-centric tasks. Before we begin, please consider that the presentation's primary audience is intended for developers of ACIS-enabled applications who want to multi-thread ACIS-centric tasks. Hence, the presentation is rather technical with several C++ code snippets. There are many examples of ACIS-centric tasks in ACIS-enabled applications. Examples include the computation of exact bounding boxes of multiple entities such as bodies or faces, the subtraction of half space among multiple bodies, and the detection of clashes among multiple bodies. Because these examples often involve computationally intensive tasks with lists of many entities, they are ripe for multi-threading. As seen in the slide, a typical code structure involves the calling of a function in a loop that invokes a repetitive task, which operates each time on a different entity. If the task for each entity is independent of all tasks for the other entities, then the entire workflow is a candidate for multi-threading. However, what seems straightforward can be difficult to implement in the context of real-world modeling applications. First, one must maintain relationships among BREP technologies, relationships that must not be disrupted by parallel tasks via multi-threading. Second, the modeling steps must be tracked and maintained in a history stream for rollback functionality. Therefore, parallelization cannot interrupt the history stream. Third, customer feedback over the years has demonstrated that the long-standing interface for multi-threading in ACIS with class thread, work, base is complex to implement. Hence, some customers have heretofore not implemented multi-threading, although their applications could benefit from it. For these primary reasons, Spatial decided to mask the complexity of implementing thread, work, base while maintaining BREP relationships and the history stream integrity by introducing a new, easy-to-implement interface for multi-threading qualified ACIS-centric workflows. The new interface for multi-threading has two main parts. The first part consists of a public base class called workPacket with two data members for error status and history stream, as well as two virtual methods. The first virtual method, called process, defines a specific ACIS-centric task in a derived class of workPacket. For example, the Boolean subtraction of entities like bodies. The second virtual method, called createWorkingCopy, creates a deep-down copy of the input entity to the specific user-defined task in process so that the worker thread can operate on that copy without affecting its progenitor. The second part of the interface is the helper function, API process MT. This function concurrently processes an array of user-derived work packets of the workPacket base class, each with its own specific task defined in the method process. The function API process MT ensures that all derived workPacket objects are processed in a thread-safe manner. The interface for the base class workPacket, its virtual method process, and the template for API process MT are defined in the new header file processmt.hxx in the newest ACIS package from Spatial. The new helper function API process MT masks the complexity of the existing class thread work base for the multi-threading of ACIS-centric tasks in ACIS-enabled applications. So what actually happens behind the scenes of API process MT? Well, calling to API process MT invokes several actions. First, API process MT creates an on-demand temporary thread pool. The number of threads is determined either by a priority during initialization of ACIS during the start of an ACIS-enabled application, or via an argument of API process MT. Second, API process MT creates a producer-consumer queue derived from the long-standing base case thread work base, and schedules work packets to worker threads. Third, API Process MT processes all work packets in a thread-safe manner. Any errors are reported back to API Process MT on a per-work packet basis. Fourth, API Process MT ensures that the main thread waits until all operations in worker threads are complete before continuing any downstream operations. Fifth and last, API Process MT merges all work packets history streams into the master thread's history stream. All of the actions invoked by API Process MT incur no performance penalty with respect to class thread work base for multi-threading in ACIS. In other words, no performance penalty occurs whether one implements the new interface via API Process MT or the long-standing interface via thread work base. Now consider a concrete example that demonstrates the implementation of API Process MT. Imagine an ACIS-enabled BIM application for the design of multi-story office buildings. User functionality is envisioned that quickly isolates geometry on specific stories of the building. Such functionality entails the fast Boolean subtraction of a half space. That is, splitting bodies along a plane and separating the pieces depending on which side of the plane they lie. Subtraction proceeds body by body, perfect for a multi-threaded process. The first step in the multi-threading process for this example is the derivation of a new class, named half-space work packet, for half-space work packets from the base class work packet. The implementation includes the definition of data members, body input, and body result, as well as data members for both the position and normal of the half-space plane. The implementation also defines a new process method for creating the half space and then subtracting it from each input body. The second step entails the instantiation of an array, HSWPS, of half-space work packet objects of type half-space work packet using the standard template library. The array is then sequentially filled by initializing every work packet with one input body and the half-space position and normal. In addition, a new function called half-space concurrent now encapsulates the first two steps for modularization purposes. The third and last step involves passing the array of half-space work packet objects to the helper function API Process MT for parallel processing. The number of threads can be defined via API Process MT as additional argument. See header file for processmt.hxx for details, or earlier when ACIS is initialized during application start. An array of result bodies is then defined and filled with the body result members of each successfully processed work packet. The resulting bodies from the half-space subtraction are then saved to a file. That is all. Nothing more is needed to concurrently subtract bodies from the half-space. The half-space in this case corresponds to a particular story of the office building in the ACIS-enabled BIM application. The whole purpose of multi-threading is to increase performance. So how does the new interface actually perform in the context of our half-space example? Consider a BIM model with 29,000 bodies and the subtraction of a half-space with different numbers of threads. The performance results in terms of computation times are shown in the table shown here and range from almost 14 seconds for one thread to just under 1 second for 24 threads. Similar performance gains can be expected from other ACIS-centric examples. Now we are ready for a quick summary of the new interface for multi-threading ACIS-centric tasks in ACIS-enabled applications. Overall, the implementation of the new interface is easy, intuitive, and quick compared to the long-standing interface via the underlying thread work base class. Let me briefly review the implementation steps for the new interface. First, Define a specific work packet for an ACIS-centric task by deriving a user-defined class from the work packet base class and overriding the process method. Second, instantiate and initialize an array of work packets. Third, call the new helper function API process MT. Fourth, check status and consume the results. The new interface entails virtually no coding overhead. In fact, compared to the existing interface, there is actually less code, which means that it is easier to read, debug, and maintain. As a result, developers of ACIS-enabled applications can incorporate multi-threading of ACIS-centric tasks quicker, resulting in faster time to release. Furthermore, no performance penalty is incurred vis-a-vis the long-standing interface with Thread Work Base. In effect, the new interface with API Process MT encapsulates the complexities of Thread Work Base, but with no additional performance cost. Although the new interface for multi-threading certainly entails less complexity, there are some limitations. In particular, the new interface offers less control because it masks the complexity of Thread Work Base. Nonetheless, if a developer wishes to have more control over multi-threading, then the long-standing interface, Thread Work Base, is always available. Two specific details regarding synchronization time and merging of history streams must be mentioned. First, for synchronization time, no manual control is offered by API Process MT. However, manual control is offered by the new class Work Packet Queue. In fact, calls to API Process MT invoke the constructor of Work Packet Queue. The new header file, processmt.hxx, in the ACIS package has full implementation details of Work Packet Queue. Second, for the automatic merging of history streams in each worker thread into the main thread, no manual control is offered by API Process MT. However, as mentioned previously, the long-standing interface, Thread Work Base, is always available for such control. Visit spatial.com for more details and contact us with any questions you may have.